So next we want to consider how to perform integrals of functions that involve logs. So first I want to note that we can actually extend our derivative rule for logs to negative numbers as long as we put an absolute value around the x. So if we put an absolute value around there, now the domain is all x values that are not equal to 0. So before we had to have only positive values. But when we put absolute value around there, well, if you plug a negative in, it changes it to positive. And the derivative remains the same. So then every differentiation formula will have an antiderivative or integral formula to go with it. So if we integrate this side, we should get back to the log function. And that's exactly what happens. The indefinite integral of 1 over x dx is natural log absolute x plus a constant, as long as x is not equal to 0. And then remember that if we took the derivative with respect to x of natural log of a function g of x, that we got g prime over g. So g prime of x over g of x. So that means that if we were to integrate the g prime over g, we would get back to the natural log of g of x. And that's this formula here. So the indefinite integral of g prime over g, if we use a u substitution here, if we let u equal g of x, then our bottom g of x is u, and then our g prime of x dx right there, that's our du. So the antiderivative of du over u is log absolute u plus c, and then u is g of x here. So if you look at the two opposite ends here, do the antiderivative of g prime over g, you get log of absolute value of g plus a constant. And that's the integral rule that corresponds to this derivative rule. So let's go ahead and put this to work. So anytime that you have a function on the bottom and its derivative on the top, you should be thinking logarithm. So here I see I've got an x squared on the bottom and an x on the top. So I'm going to do a u substitution here. And I'm going to let u be 2x squared plus 1. So then my du is going to be 4x dx. And then up here I've got 3x dx. Well, let's go ahead and take that 3 on the outside there. So I'll have 3 times the integral of x over 2x squared plus 1 dx. And then I'd like to have 4x dx. So let's multiply by 4 on the inside and then multiply by 1/4 on the outside to compensate. So I like to multiply for what's missing and then compensate. If you want to, you can just divide both sides by 4, get 1/4 du is x dx. That's the other way to do it. So then 4x dx right there, that's our du. And then 2x squared plus 1, that is our u. So this is just 3/4 out in front. And then it's integral of du over u. So now that's this guy here, and that's log absolute u plus a constant. So we've got 3/4 out in front, natural log, absolute value of u plus a constant. And now we go ahead and plug our u back in. So 3/4, natural log, absolute value 2x squared plus 1, and then plus a constant. And then x squared is always positive, multiplied by 2, always positive, plus 1, always positive. So we actually can simplify this. We don't need the absolute value. We can just use parentheses. So this will be 3/4 natural log, 2x squared plus 1, and then plus a constant. And that's our antiderivative. Again, the key is you're looking for something that looks like g prime over g. Function on the bottom and derivative on the top. And let u equal the bottom.